Okay. So I would like to thank the president of my defense committee, Patrick, for the kind introduction. And I would also like to thank all the members of my defense committee for being here today for my talk, which will revolve mainly around motions and how we can plan them for anthropomorphic systems. So let us talk first about motions. So a motion is basically a function or the link between time and space. So if you look at this particular motion, so which is a jumping, kind of jumping back motion, while the time is moving continuously, so are the positions of the robot. And so this is what we define as a motion. Now we would like to plan motions for anthropomorphic systems, which are a particular class of systems. And generally speaking, they are systems that are made to look like humans. So usually they will have 2 legs, 2 arms, sometimes even a head. And so this class includes either digital avatars, so in the case of computer graphics, or humanoid robots in the case of the real physical world. Now there are a certain number of constraints that any motion for such systems need to obey, such as mainly balance constraints. So balance can be very crucial for such motions, and balance can either so the loss of balance can lead to the loss of physical integrity of the robot if it falls down quite badly. There are also other constraints that need to be taken into account, especially when we have external environment, such as obstacles here. So we need to make sure that we do not have any collisions between the limbs of the robot and the external obstacles. And we also need to make sure that we do not have any collisions intercollisions between the different limbs of the robot. And this is very crucial for anthropomorphic systems, since they are highly redundant systems. So we could have very easily collisions between the feet, or between the hands, or between the feet and the hands, and so on. So using such anthropomorphic systems, the advantage is that we can plan a wide panel of motions, either by considering a humanoid robot by itself or in collaboration with other robots. So of course, I will almost, in this thesis, I wasn't able to plan any of those motions, but this is a very wide panel of what we can hope to do with humanoid robots. So then I'll move on to how we can plan some, at least, of these motions. So the main approach that we consider is that instead of planning motions in the 3D space of the robot, of the system, we will place ourselves in a simpler, an easier space that we can consider. So, and this is what we call the configuration space. So a configuration space is such that each point of the space represents uniquely the whole position of a system. So in the case of a humanoid robot, you will have a part of one configuration which will be made of the different, for example, angular values for each joint of the robot, so located usually at the motors. And a part of this configuration will be dedicated for the whole, the general placement of the robot in its space. Now, it's not very easy to right away, starting from a configuration QS and a configuration QG and an obstacle map, so here in the configuration space, it's not easy to find straight away a trajectory, so motion linking time to space. So it's usually easier to place ourselves in a simpler configuration space that corresponds to a simpler robot, or simpler system. So this system might have less degrees of freedom, or it might even have less constraints or constraints that are easier to handle. Now, in this particular space, once we are able to define it, we can rely on sampling-based planners, which are able to rely on randomness, so on sampling random configuration in the space, and on very fast exploration of the space, even if it's highly dimensional, in order to find a continuous path this time, so not a motion, not a trajectory, a continuous path linking the original configuration to the final one. And so here it's important to note that we do not have yet any time parameterization. There is no notion of time. The S parameterization here could be arbitrary. Now, once we have found such a continuous path, which is collision-free, so we are avoiding the collision space regions, we can then move back to the original space of the system and either approximate or continuously reshape this path in order to transform it to a feasible trajectory on the original system. So here we are back to having the notion of time. So, and this is what describes what we call the decoupled approach. So it renders the motion planning problem a bit easier to solve. Now, during my thesis, so in the past 3 years, my work has revolved mainly around this decoupled approach, around different contributions, which I will show here. So in the first contribution, I developed a path optimization technique when we are using the bounding box approach for a walking humanoid robot on a flat surface. In the second contribution, so I do not consider a bounding box, but the whole body geometry of the robot. But we consider a specific kind of constraint, mainly static balance constraints, where we just look at how the center of mass is moving, and we consider in this case that we have a fixed set of contact points. And we can rely on special implementation of RRT, or rapidly exploring random trees, to find continuous path for such systems and then transform it through optimal control methods to a feasible trajectory on the robot. In the third part, we actually consider a different set of constraints where the robot can slide on a flat surface in its environment. And so we can also rely on sampling-based planners to find continuously sliding path for the robot. And once we have that, we rely on a nice property from optimal control theory to transform this continuous path, which is not admissible, to a trajectory that is feasible by the original system. Now, I would like just to note that compared to my manuscript, these two parts were inverted. So let us move on to the first part, which is about path optimization for the bounding box approach. Now, there exists already a decoupled approach where which is called the bounding box approach, which consists in simplifying planning by considering only 3 degrees of freedom for the robot, so x, y, and theta, so the orientation in the horizontal plane, and considering a geometrical bounding box that includes all geometries of the robot as well as some of the swaying motion of the robot. And here's an example of what we can do with such approach using, for example, sampling-based planners. So we can find a continuous path connecting QS to QG. Okay. And so once we have found a path for the bounding box, we can actually place a set of footprints along the path that we found in order to prepare ourselves for planning footstep motions to go from the original configuration to the final one for the complete system. Now, of course, before we can generate motions that will connect the different footprints, we need to define what is the concept of balance for a walking system. So for the particular case of walking humanoid robots on a flat surface, there exists a criterion which is called the zero moment point, which is defined as the point on the floor where the horizontal components of the reaction forces moment is 0. And so this point basically, there exists, a sufficient and necessary condition for balance in this case, which is that the ZMP remains during the whole motion strictly inside the convex hull of the contact points, or which is also called the support polygon. Now, if you consider the whole robot, and if you want to compute its ZMP, the ZMP is rather simple, rather difficult to control. So, for the case of walking robots, we consider a reduced dynamic model, which can still grasp a large part of the dynamics, which is called the cart table model. So it consists in concentrating all the mass of the robot inside, so in a point. So we consider a point mass that is represented here by a cart that is moving horizontally at a constant height on a table. And so the foot of the table has the same width along one dimension that the width of the support polygon of the robot. Now, once we consider such dynamic system, we can write very simply the ZMP as this expression, which defines an ordinary differential equation for the center of mass. We can see that we have the center of mass, so horizontal coordinate, as well as its acceleration. Now that we have that, we can actually go back to the footprints. Since we know that the ZMP needs to remain all the time inside the support polygon, we can actually devise very easily a trajectory for the ZMP such that it remains inside the support polygon defined by 2 feet during a double support phase, and where it moves to under 1 foot, so that the other foot can be lifted and land on on the next footprint. And once we have again a new support polygon, we can move the ZMP continuously to the right footprint, and so on, until we find completely the ZMP trajectory. Once we have the ZMP trajectory, we can rely on a preview control-based pattern generator, which will allow us to solve the previous equation of the ZMP and derive the center of mass trajectory. And once we have the center of mass trajectory, we can rely on inverse kinematics methods to generate a trajectory for the whole body of the robot. Now, this is a summary of the whole method, so we can rely on RRT method to plan a path for the bounding box. We could eventually use shortcut optimization to try to shorten the length of the path. And once we have this path, we can rely on footprint placement and then the pattern generator to obtain a walking trajectory, as we see here. So in this example, we have the robot which starts at this point and has to go to another point of another room of the apartment. And so it has to find a walking motion from here to here. And now, if I move to an interesting point of the trajectory, so we can see here that, sorry for that, I'll go back. Okay, so we can see here that the robot is moving laterally, so it will move laterally all along this portion of the space, whereas while the environment is not very constrained, and so it will do a series of lateral steps. And experimentally, we have observed that humanoid robots that we have walk laterally much slower than they can walk forward. And so this is a bit bad because it means that we will have a trajectory that will take a long time to be executed, as you can see here. So, and this is mainly due to the random nature of RRT, because the orientation of the robot is mainly due to the orientation of the bounding box that we found with RRT. And so as I said before, we need forward walking because it can lead to shorter trajectories in walking time. And also because if you want to, so here we do offline planning, but if you want to consider perception and so closing the loop between perception and planning, usually it might be needed to use cameras, and cameras are usually located in the head of the robot, and they face the roughly the walking direction. So it can be interesting to optimize the path that we have obtained in order to give certain favor towards forward walking. So the contribution here is that we introduce a new kind of brick that you will insert in the existing planning framework in order to minimize the walking time. So let us reconsider the path that we have obtained here. So at any point of the path, we can, through linear interpolation, find a current orientation. As you can see here, it can be completely arbitrary. So we define additional orientations for the bounding box by keeping the x and y coordinates. So we define front orientation, which is tangent to the path, and we define the two possible lateral orientations, which are where the direction of the bounding box is orthogonal to the path. And with that, we can execute an A-star algorithm that will allow us to find a path that minimizes the walking time. So here we see again the same path that I showed before, only along one dimension, so connecting QS to QG. We will define a sampling distance, thanks to which we will evenly sample the path with sample configurations. And on each sample configuration, we will have the current orientation, and we will use also the other, frontal and two lateral orientation that I defined earlier. And with that, we can run an A-star algorithm that will expand the graph of possible transitions. And of course, it will disregard sample configurations that lead to collisions, as well as arcs that lead to collisions. And so the A-star will continue running until it can find a path, P-opt, that is different than P, where we have minimized the cost of the total path. Now, of course, we need to define what is the cost that will be used with the A-star algorithm. In order to, what we want to do is make the robot go forward as much as we can. And so experimentally, we have observed that the robot walks faster in frontal motion. So what we can do is define a constraint. So it's it's a virtual constraint. It doesn't really exist, but it's a virtual constraint that allows us to say that the forward speed is actually, here we have the bounding box, and that's the tangent path. So we have the forward speed that is greater than the lateral speeds, as well as the backward speed. Now, constraining the backward speed does not make a lot of sense, but because kinematically speaking, the robot could walk backward without any problems, and it can walk as fast as frontally. But if you want to, for example, use the cameras, we need to walk forward the whole time. So we define those VF max, VLAT max, and VF min. And so we define the constraint on the speed, where we have the maximum speed defined by two half ellipses. And once we have this constraint, we can, for two configurations, QI and QJ, compute the walking time as the integral of 1 over the maximum speed at each point. And additionally to that, we need to define a heuristic function for the A-star such that it is admissible. And so we define the heuristic function as the cost of walking frontally from QI, so any configuration, to the goal configuration while staying on the path P. So with this, we can resolve the same problem. So in this particular case, I show two trajectories that are superimposed. So one trajectory which corresponds to the stepping motion found without the regular sampling optimization, which we see here, and here the one with regular sampling optimization. And as you can see in this part particularly, the robot is oriented such that it is tangent to the path that we found, and hence it is much faster. And so that's the robot that we saw earlier. It's still trailing behind, trying to reach the other one. So here we show a summary of the results that we have that we executed for different environments. So what you should memorize from this table is that for the regular sampling optimization, so when we insert it, we have a certain computation time of a few seconds that is added to the existing decoupled approach time. But if we look to the walking time that we gained, we can see, for instance, that for the apartment scenario, we have gained 80 seconds in walking time. So here we've lost 2.4 seconds in the computation time, and we've gained 80 seconds in walking time. So which is very interesting. So in summary, the regular sampling optimization consists in evenly or regularly sampling a path with sample configurations and defining at each sample configurations 4 orientations. And once we have that, we can run an A-star search with time given as a cost function and find in this particular graph, so for the given orientations and for the given sampling distances, we can find the minimum cost path. And as I showed earlier, we have optimized trajectories which are shorter with respect to walk time, and we have a very low computational overhead to the planning scheme when compared to the walking time that we have gained. Now, the bounding box approach is very interesting because it allows us to plan quite fast walking motions. So, for example, inside apartments, as I showed earlier. Now, but still, it's a conservative approach. So if you want, in this particular case, to move the robot from one point to another of the room, and the RRT has found a path such that the bounding box is sliding and moving laterally between the two chairs, well, we will obtain a trajectory such as this one, so a final stepping motion. And as we can see, so as we can sense, the robot could have just simply lifted its arms, if it could, to just keep walking forwards and avoid the collisions with the chairs. So what we argue here is that we should consider the whole body geometries of the robot when planning, which leads us to whole body optimal motion planning. So I'll go back for a few moments to see a bit the inner workings of the RRT. So the RRT, which is, or rapidly exploring random trees, are a kind of sampling-based planners. And so they rely on an iterative exploration of the space, where in each atomic step, we will sample a random configuration, look for the nearest configuration in the existing tree that we have expanded, and then extend iteratively from Q near to Q round until either we reach Q round or there is a collision. And in this case, we keep the last configuration that is collision-free, and we can add Q new to the existing graph, T, and as well as the edge connecting Q near to Q new. Now, if you want to consider planning whole body motions for a robot, so if we have to consider the fact that during the whole motion, there are some limbs or bodies of the robot that are constantly in contact with the environment. For example, we might have the 2 feet, which are constantly in contact with the walking surface. So when we have contact constraints and we also have static balance constraints, it consists on planning on a zero-measure manifold. So we cannot really explore the whole configuration space. We need to explore a specific sub-manifold of this configuration space. And so in our case, we will consider that such manifolds can be expressed as the set of solutions or roots of the function f, so a vector function f, which is made up of these constraints. So now that we have defined this manifold, we still don't know how to plan on it, so we have to modify the RRT. So there exist variants of the RRT where we can take constraints into consideration, and where we can plan, so explore very efficiently constrained manifolds. So it consists of slightly modifying the extension phase of the RRT, where we still sample a random configuration. We look for the nearest neighbor, and then so we will do very simply linear interpolation to get those samples. But of course, these samples are not on the manifold, because since we have a zero-measure manifold, the probability of sampling Q round or obtaining those configurations on the manifold is 0. So to go from this configuration to another one that is on the constrained manifold, we can rely on Jacobian-based inverse kinematics methods that will basically, starting from this configuration, start a Newton-Raphson method that will iteratively look for the root of this function, and once f of q equals 0, this means that we are on the constrained manifold. And since we are following the Jacobian, this means that we are doing a projection straight on the manifold. And so we do this iteratively until either we reach the projection of Q round or until we hit an obstacle. And in this case, in both cases, we keep the last configuration that was collision-free, and we add it to the existing tree. So using this constrained RRT, we can, for example, plan statically balanced path, where we define the planning manifold as the intersection of several manifolds. So here we have a manifold where we constrain the right foot to remain at a fixed 6D position. We also fix the left foot at another position, and we constrain the center of mass vertical projection to be at the center of the support polygon. So as you can see here, we can plan a continuous path, so where we have different set of milestones from the lower shelf to the upper shelf. Now, basically what the constrained RRT does is that it inherits all the properties of the standard RRT. So it allows us to generate quasi-static collision-free path. It is probabilistically complete, so it has been proven to be so. And it allows us, so since it's a global planner, it allows us to avoid getting stuck in geometric local minima. Now, it also inherits the drawbacks of the RRT, which is that it could lead to random and long paths. But what we can do still is rely on shortcut optimization methods to try to shorten the path a bit. But still, so we have found a path. So there is no time parametrization, and we still don't have a trajectory that we can execute on the robot. So we need additional processing to obtain a feasible trajectory. So to do so, we can rely on numerical optimization methods for optimal control. So here we have an example, so a rather generic example of optimal control problem. So basically what we want to do is find a trajectory such that we minimize function, which we call the objective function, under constraints that the differential equation of the model is always verified, and such that we could have equality constraints and inequality constraints along the path, so for the whole duration, as well as terminal constraints, so initial and so boundary value constraints, initial and final constraints. And so we usually what we do here, so one way of solving this problem is to rely on Jacobian-based numerical optimization methods, which will iteratively start from a given initial guess of a trajectory, then iteratively converge to a trajectory that minimizes the cost function. So it can allow us to generate locally optimal trajectories by a continuous reshaping, while enforcing a set of constraints. Now, it has some drawbacks due to the fact that it's local, so it can get stuck in local minima, and so we sense that the success of such methods depends on the initial guess that we provide to them. And so this suggests that we need also prior processing to guarantee the optimization success. So what we propose here is to define a new decoupled approach, where we will first plan a draft path using a constrained path planner that I showed earlier, then optimize it using numerical methods for optimal control. And so this will allow us to generate locally optimal collision-free trajectories. And in our case, we applied them to a humanoid robot, which had fixed coplanar contact points. So we consider that the floor is flat, and we have both feet on the floor. Now, keep in mind that as we provide as an initial guess to the optimal control problem, so the constraint path that we found, it will be iteratively reshaped until we minimize the function. So, and during this minimization, we need to make sure that we still avoid the obstacles and we still avoid self-collisions. So to do so, we propose to represent each body of the robot by a capsule, which consists of the set of points lying at a distance r from a segment. And the advantage of using such a geometry is that it's very simple to implement. So it's a very simple geometry. And with it, we can very easily compute the distance between either two capsules or between a capsule and a mesh. And this can be done very fast. And furthermore, we can have, for slight penetrations, we can compute a penetration which is basically leads to a negative distance and can be very useful during the optimization process, since we rely on the Jacobians. Now, to avoid setting by hand each capsule parameters for each body of the robot, we propose to solve an optimization problem for each body, where we minimize the volume of the capsule, and so we look for the capsule parameters such as we minimize the volume, while making sure that the points of the original mesh, of the underlying mesh, remain inside the capsule. So, because we want to find a bounding capsule which is conservative. Now, of course, this optimization problem is non-convex, so it can only lead to a local optimum and not a global one. But we have observed that still the capsules that we obtained are quite convenient, especially that the robot geometries are roughly cylindrical, so it was more than enough for our application. And here we can, so once we have that, we can define the full optimal control problem, where in our case we decided to minimize the integral of the squared jerks in order to obtain trajectories that are smooth. And we need to take into account the joint constraints, so mainly the position limits, as well as the velocity limits, as well as the joint torque limits. And since in the first part we had planned on a constrained manifold where we had a fixed position for the 2 feet, we include those 2 kinematic constraints here, where we constrain the position of the 6D position of each foot to stay constant during the whole motion. And so before we took into account static balance constraints, but now we will take dynamic balance constraints since we are generating a trajectory, and we constrain the ZMP to remain inside the support polygon. And to ensure that we don't have any collision or self-collision avoidance, we add vector constraints where we constrain the distances to be positive between the obstacles. So we're using the capsule representation that I showed earlier. Now, particularly we use MUSCOD, which is a specialized direct multiple shooting solver for optimal control. And it relies on a specially tailored sequential quadratic programming solver that will take advantage of the sparsity of the Jacobians and the Hessians to solve quite efficiently the optimal control problems. Now, in order to rely on SQP methods to solve an optimization problems, we cannot simply provide, say that we want to minimize, find a function that minimizes a certain objective function, because the space of the functions of the possible function is infinite dimensional. So we need to find a proper discretization or parameterization for the controls in order to obtain a finite dimensional problem. So to do so, we choose to represent the jerks as a continuous function that is piecewise linear over a set of 20 sub-intervals over time. And so similarly, the constraints are also discretized over each of the nodes of the trajectory. So here we have a first example that shows that where we planned a motion, where we planned a path using a constraint planner, and then we rely on MUSCOD to solve an optimal control problem that I showed earlier. So it's interesting to mention that this motion is run in real time, so there was no acceleration. So the motion is really fast. And to the left, we can see the evolution of the collision avoidance constraints. So basically, these are the distances and they are, so I must mention that they are only enforced at the 20 discretized nodes. So in between we might have some constraint violation, but we have observed that it was not very high. But otherwise we have a kind of saturation here for these constraints. And to the right we can see the evolution of the ZMP in red. And we can see that it stays inside the polygons, the support polygon defined by the 2 feet on the ground. Here we show its second motion, which is a bit more difficult because we have a constrained environment with external obstacles. And so here we first plan a constrained path, and then we optimize it in order to make the robot grab a ball in the lower shelf and displace it to the upper shelf. So in summary, what we present here is a decoupled approach, which consists in first planning a draft path that was provided by the constraint planner, and then giving this path as an initial guess to be used by the numerical optimal control solver. And so this allowed us to generate trajectories which are locally optimal, feasible, and collision-free. However, so during our use of such method, so we basically relied on a black box where we just give the formulation, and it will allow us to solve the optimal control problem. And we have observed that even with a proper initial guess and duration for the trajectory, we still have some failures for the solver. And it was very difficult for us to tune this solver, tune the different parameters, especially the scaling, in order to have a proper convergence rate and lead to a proper success rate also. And furthermore, we obtained very long computation time in order to generate those motions. So for example, for the shelf environment motion, the motion generation took more than 30 minutes to go from the initial guess to a local optimum. And also we feel it's difficult to extend to walking motions. So because what we consider here is a phase where we have a fixed set of constraints, so a fixed set of contacts. Now, to generate walking motion, one solution would be to look for contacts and then optimize on different phases. And this is, for example, a work that has been done by Longagne and colleagues, but we feel it feels like it's very difficult to do. So what we propose to do in the third part is to actually consider a simpler system here to the right, where we have less constraint and we make the robot slide. And thanks to a nice property from optimal control theory, we can generate whole body dynamic walking trajectory. So here we have walking. So in this example, we have used the same constraint planner that I introduced before in the second part, where we have less constraints. So the feet are allowed to slide in the environment. And here we have a set of floating objects, and the robot is able to lift and move its arms in order to pass through them. Now, of course, we need this path that we found is not executable directly on the robot, because the path is sliding, and we need to kind of convert this path to a sequence of stepping motions. So I'll first introduce the notion of small space controllability of a system. So a system is said to be small space controllable if, for any configuration of the system and for any positive epsilon, for any arbitrary one, there exists always an eta, such that for any configuration Q prime inside this ball of center Q and radius eta, there exists a trajectory that will go from Q to Q prime while remaining entirely inside the ball of center Q and radius epsilon. So what this suggests is that for an arbitrary boundary that we set for the trajectory, we can always find, starting from Q, a Q prime in an open neighborhood around Q that we can reach. And so using this result, it can be proven that any collision-free, not necessarily admissible path can be approximated by a sequence of collision-free feasible trajectories for small space controllable systems. So we can see here as an example that we start with a continuous path that is not necessarily admissible. And thanks to the small space controllability property, we can always find a sequence of jumps, kind of, that will allow us to arbitrarily closely approximate the original path. And what is very interesting is that in the first part, we rely only on purely geometrical reasoning. And once we have a continuous path, we have the formal guarantee that we can always find a collision-free, feasible trajectory for the considered system. Now, this result is very interesting because it could help us approximate the sliding path by a sequence of walking steps. So the question is a walking humanoid robot small space controllable? So first, we consider this simplified model of humanoid robot where we have the center of mass at a height ZC, and we have the 2 feet, which have along the y-axis a width lowercase l, and each foot is located at a distance uppercase L from the projection of the center of mass. Now, if you want to prove that such a system, so here we consider static robots. So if you want to prove that such a system is small space controllable, we need to prove that, for example, we can lift the foot and put it back arbitrarily closely to the original foot, while making sure that the center of mass does not move, stays inside an arbitrarily small neighborhood of the original position. Now, if we consider a statically balanced robot, the center of mass projection needs to be constantly inside the support polygon. So if you want to lift the foot and put it back very close to it, we always need to move the center of mass first over the left leg, and then once we put back the right foot, we can move the center of mass back to its original position. And the problem is that however small this variation is, this motion is here, we cannot bound the center of mass motion in an arbitrarily small neighborhood. So this proves that a quasi-statically walking humanoid robot is not small space controllable. Now, on the other hand, if you consider a dynamically walking robot, and if you consider the card table model, where we have these equations that I introduced earlier, if we set the center of mass to have a sinusoidal variation with a frequency omega and an amplitude epsilon, we can compute the ZMP as following. So we obtain also a sinusoidal wave of frequency omega, but we can see here that due to the double differentiation here of this term, we have the frequency term that appears inside the amplitude. So the higher the frequency of the center of mass is, the greater the amplitude of the ZMP is. So this suggests that moving the center of mass fast enough in an arbitrarily small neighborhood generates dynamically balanced walking. So if we look back at the same example, at the same simplified model, we can see that we can, using the same signal that we showed before plus a transient state, we can show that we can move the ZMP back and forth, during time, from the right leg to the left leg, such that we can lift one foot, put it back, and then lift the other, execute walking steps, while making sure that the center of mass remains inside an arbitrarily small neighborhood of its rest position. And so this proves that a dynamically walking humanoid robot is small space controllable. Now that we have this property, we can actually, starting from a sliding path, so where I show here the original center of mass path, we can start by executing steps with any length. Now, of course, since the center of mass deviates, so when we rely on a pattern generator, as I showed earlier, we might have collisions that will occur. So now that we have collisions, we can actually cut the path in half, so keep the parts that are collision-free, and then start again. And once that we have steps that are very close to each other, we can reduce the step length of the robot, which will lead to faster, to a higher frequency of the center of mass and hence lower amplitude. And we can continue to do so until we have no more collisions. And as you can see here, the swept volume does not touch the obstacles. And also we can see that in a narrow passage we have a high frequency of the center of mass, but we are still able to execute walking, through the small and fast steps. And here is the same approach executed on the previous example, where we start with a sliding path and we execute, we obtain stepping motions, sequence of stepping motions. And as you can see that here, that when we are close to obstacles, we have small steps. Whereas when the environment is not constrained, the robot executes what we call nominal walking. And when we reach again a new obstacle, there will be again small steps that will be executed to avoid collisions. And the nice thing is that this always works. Okay. So here's a second example where we have a shelf. So we first find a sliding path between the table and the lamp. And we can see that if we use nominal walk parameters for stepping, we will have collisions. But if we use a control strategy that reduces the step size, we will have small steps and we will not have any collisions. And here we can see the same example, the same motion executed on the real humanoid robot HRP2. So the HRP2 is holding a ball and it has to release it inside the shelf. And so once it reaches the vicinity of the lamp, so the narrow passage between the lamp and the box, it will execute small steps and then it will go back to executing nominal walk pattern until it reaches the final configuration. And what is nice here is that we have a seamless integration between navigation and manipulation. So at no point did we mention that we have a navigation mode and then a manipulation mode. Everything is done together. So in summary, we have proved that a dynamically walking humanoid robot is small space controllable. And this has allowed us to, again, devise the decoupled approach where we first plan a draft sliding quasi-statically feasible path. And then we rely on this small space controllability property to approximate it with a sequence of collision-free steps. And one interesting point is that it allows us to combine navigation and manipulation seamlessly. And when we compare it to the approach that we used in the second part, this approach is much simpler, in my opinion. It's more reliable by experience, and it's faster than whole-body optimal control. So this concludes all the parts that I introduced, and we reached the conclusion of my talk. So I'll first start by a summary of my contributions. So first, I devised the path optimization method for humanoid walk planning when using the bounding box approach. And then I moved on to combining constrained path planning methods with optimal control methods for the generation of locally optimal collision-free trajectories. And finally, we generalized so the constrained path planning that was introduced here to walk planning using the small space controllability property of a dynamically walking humanoid robot. And finally, I would like to note that all contributions were used to generate actual and feasible motions on the HRP2 humanoid robot. So what I would like to argue finally is that using the decoupled approach for motion planning is very nice because it leads to easy planning, fast planning, and sound planning. And also I would like to argue that instead of generating complex motion for complex dynamics, it is still interesting to focus on simpler systems that represent quite well the original one, find equivalence properties that will allow us to solve efficiently and reliably a particular class of motion planning problems. And finally, I would like to end with some open questions. The first one is, how can we execute trajectories reliably in uncertain environments? So what this question suggests is that, actually everything that I did was done in offline. So once we find a trajectory, we need to execute it on the actual platform. And sometimes we might have either obstacles that are not very well modeled, or even the dynamics of the system might not be very well modeled. So this asks the question, how can we execute trajectories reliably? And what I would like to argue here is that we could, for example, use the decoupled approach, but not only for planning. So we could, for example, use the first part of the decoupled approach to plan a draft path for a very simple system. And then once we have found this path, we could rely on the online controller to either reshape or approximate this collision-free path if we have the right properties, in order to generate a trajectory that will always be feasible on the robot, regardless of the uncertainties in, I don't know, for example, the obstacles, the contact forces, and so on. Now, the second question that I'd like to ask is, we saw that the small space controllability property is very nice. It's very useful, especially for generating dynamic walking motions, but on a flat surface. And the question is, can we extend this property to multi-contact motion? So if we imagine that we are still, for example, walking on a flat surface, and we want to use the robot's hand to take support on the wall. Can we imagine planning a sliding path for this robot that is in contact with different surfaces? And can we, so if we prove the same small space controllability property, we could, once we have this draft path that we can plan very easily, transform it, so approximate it with a specific guarantee by a sequence of multi-contact steps. So these two questions, in my opinion, can make very interesting future work topics. And with this, I would like to thank you for your attention and my talk with a small video. Thank you.
Thank you. So now we will start the scientific